a powerful tool of modern cosmology. Dan Coe, a staff astronomer at Space Telescope, has made masterful use of strong lensing clusters to explore cluster mass distributions and, most remarkably, to discover galaxies at very high redshift. In fact, Dan discovered a strongly lensed galaxy at a redshift of a mere 11. Dan will discuss the implications of this amazing object that we see as it was when the universe had an age of about 400 million years. It is my great pleasure to welcome Dan Coe to describe the hunt for more of these young objects and the constraints they place on our understanding of the formation and evolution of structure in the universe. Dan.
Thank you very much, Margaret, for the great introduction and for hosting me here at Harvard. It's actually my first time visiting. It's been a great visit so far. And thank you to Sean and Charlie for inviting me here. Right, so I'll be talking about hunting the first galaxies with gravitational lensing. So Hubble is celebrating its 25th anniversary. And over these 25 years, it has observed galaxy evolution over 13 billion years. From the Hubble sequence we see around us today in the local universe, forged in part by these galaxy mergers, which we see in this simulated animation and these Hubble images, to more irregular galaxies that we see in the distant past. As far back as redshift 8, 650 million years after the Big Bang, thanks to gravitational lensing, we see multiple clumps in a distant galaxy. At redshift 11, my candidate for the most distant galaxy yet known, 97% of the way back to the Big Bang we're looking, we see what may be a single clump. It's not quite resolved, even with Hubble and the power of gravitational lensing, magnified by a factor of 8 in this image. It's not quite resolved, so it has a half-light radius of less than 100 parsec, the size of giant molecular clouds, star-forming regions in our local universe. So this might be a building block of all the galaxies yet to come. Or it's possible with larger telescopes we'll resolve it and find even smaller building blocks. So what are some of the frontier questions about galaxy evolution? When did the first galaxies form? Estimates range from redshift 10 to 30 or maybe more. I think we're starting to carve into this range with the redshift 11 candidate. What were their properties? How did they evolve? How many were there? And all of these tie into this question, did they reionize the universe? Which I'll talk a little bit about later. Answering these questions require counting galaxies, measuring luminosity functions, and also detailed studies of individual galaxies. So I'll motivate this talk, I'll motivate why it's important to count galaxies, what we learned from that. I'll talk about the power of gravitational lensing to do that, and also I'll touch on detailed studies of these individual galaxies, including the redshift 11 candidates, some follow-up work I've been doing on that. So this is the Hubble 25th anniversary image. You can't get much more detailed than this when you're studying galaxies. This is the star cluster Westerlund 2. And this is what it might look like to fly through this galaxy cluster, or this star cluster, sorry. We see this dense star cluster in the middle, and we see that it's a mere 2 million years old. And as many youngsters do, it's pushed away its parents and to hang out with other youngsters of similar age. And by pushing away this gas, it's inhibited star formation in its immediate surroundings, but it's also made the gas more dense nearby, so it's actually triggering star formations in these nearby regions. So these are the processes that we have to try to account for when understanding galaxies on larger scales. So this is an example from the Illustrious simulation. You might have seen an animation like this. I know some people here work on this. So this is the gas temperature for galaxies that are being formed and merging. And AGN, the central black holes, violently blowing material out of the central regions and then warming the intergalactic medium, enriching their surroundings. So then the question is, when we simulate large areas of the universe like this, do they match our observations? And we can learn a lot from counting galaxies. So when we count galaxies in terms of their mass or their luminosities, we find they follow these Schechter functions. So in terms of mass, you find more low-mass galaxies, and they follow a faint end slope of alpha, have a characteristic normalization and magnitude or mass, and then exponential fall-off to larger masses. This is the stellar mass. If you look at the total mass in these systems, there's a higher mass. Most of the mass is in the form of dark matter. So if you just look at the baryons available in the cosmic average, there's about 1/6 that these halos have to work with in terms of forming stars. And then if you drop another factor of 3, you get down to sort of the most efficient galaxies in terms of forming stars. I'm going to flip this plot on its side here. So in terms of total mass, we see that Milky Way-sized galaxies are about the most efficient in terms of forming stars. And there are all of these feedback processes that inhibit star formation on these different scales, from massive stars and supernovae, AGNs, and mergers. And so we can, by counting galaxies, we can constrain all of these different processes. We can learn about them in the local universe, but then also in the more distant universe to have some idea whether these processes were similar or how these processes were different at earlier times. So an example of what we can learn from this is work from Rebecca Bowler from large ground-based imaging, degree-scale ground-based near-infrared imaging, and candidates that they observe at redshifts of 7. So this is the mass function in black, and we see that the plot is now flipped in terms of its x-axis, so the fainter galaxies are toward the right, and we do see this quenching at the faint magnitudes. So we see the galaxies follow the Schechter function below the mass function. At the higher masses, the brighter luminosities, we see hints of that there are more galaxies than expected due to the Schechter function. So these galaxies are closer to the mass function here, suggesting that the AGNs have not quenched the star formation as much as they have at later times, so that the black holes aren't as efficient at quenching star formation, which makes sense. We expect this to happen at some earlier time, although I should say this isn't that conclusive yet. There's still, we need more data to confirm this. These are small number statistics, but this is an interesting hint of the type of thing we can learn about star formation just from counting galaxies. So to discover even more galaxies at these high redshifts, there are large Hubble programs like CANDLES. Borg is a pure parallel program, the ultra deep field, and these are discovering much larger numbers of high redshift galaxies at somewhat fainter magnitudes, down to the faintest magnitudes yet observed. And the main tool we use to measure the distances to these galaxies is the galaxy colors, or their photometric redshifts. And so this is the tool that I use, Bayesian photometric redshifts, originally developed by my thesis advisor, Narciso Benitez. As you can see, as the galaxy moves to higher and higher redshift, it becomes redshifted. It drops out of these bluer bands here, and we identify these high redshift candidates as Lyman break galaxies. So people have used this to count the numbers of galaxies at redshifts 4 to 8. This is from the CANDLE survey and other surveys in the ultra deep field, like I showed before. And so this is a paper by Richard Bouwens, 11,000 galaxies at redshifts 4 through 8. And we see that their luminosity functions are fairly well constrained through, from 630 to 1.5 million years to 1.5 billion years after the Big Bang. And they're all fit to Schechter functions pretty well. There's significant cosmic variance you have to deal with. The 5 CANDLE fields are shown here in yellow on this example plot from this recent review paper by Piero Madao and Mark Dickinson, showing that you're sampling rare peaks in the mass distribution and possibly voids. So this is a nice example, illustration of this from Richard Bouwens' paper, showing that in these 5 CANDLE fields, you see different densities, over-densities or under-densities of galaxies. So you really need to sample, 5 or more fields to mitigate these uncertainties, this variance. the Borg and Hippies programs sampled many more fields, and so they reduced these uncertainties so that at redshift 8, where they're most sensitive, they sort of get the kind of the average value there with somewhat large uncertainties. You see the uncertainties increase as you go to higher redshifts, to earlier times, and this is because we're sampling the rarer high mass peaks for the magnitudes that we're observing at these early times. So as you push out to higher redshifts, you can imagine this would be even more challenging, get larger uncertainties. And what we find so far is that the galaxies at redshift 10, if you extrapolate from these redshifts, there appears to be a deficit. From work done by Richard Bouwens and Pascal Oesch and others, Steve Finkelstein, there appears to be fewer than you expect at redshift of 10. And if you integrate these luminosity functions, you get the cosmic star formation rate density. So this Lilly-Maddow plot that you've probably seen, that galaxies build up over cosmic time, and then at some point, for some reason, they run out of gas, basically. If we trace this back to the earliest times, there appears to be this dramatic evolution in the first 500 million years. And these are kind of small number statistics, and we need to work harder to confirm this, but if true, this could have implications for reionization and the first galaxies. You can ask yourself, is this, if there are fewer galaxies to observe at higher redshifts, is this bad news for people working on high redshift, for JWST, that there are fewer galaxies? And I think it could be good news in a way. If there is such a sharp drop-off, you might find that the first galaxies actually formed closer to redshift 15 or 20 rather than redshift 30. So if they formed later, at redshift 15, let's say, they'd be more within reach of study from JWST and other telescopes. So I'd like to think of it more of a glass half full type of thing. But again, this is, we still need more data to confirm this. So we're observing galaxies during this epoch of reionization, and so this is the second major phase change in the history of the universe. After recombination, we believe that galaxies started to form stars, and eventually there were enough of them that they reionized the universe through this gradual process, as we see in this simulation here. These expanding shells that then eventually merged until most of the universe was fully ionized. And so we believe that galaxies probably reionize the universe. This is my best summary of all of the results that people studying reionization. There are a lot of uncertainties involved with understanding this process, but if we take the cosmic star formation rate density from this recent work by Maddow and Dickinson, we can figure out what the history is basically of this of the reionization. So this is the Thomson optical depth. So this is, let me go back a second. If you're looking from the present day back to the cosmic microwave background, the amount of ionized universe that you're looking through, it polarizes the cosmic microwave background. So if reionization happened at a later time, you'll see a larger Thomson optical depth. If it occurred at a later time, you'll see a lower Thomson optical depth. So there was a recent result from Planck that found a lower optical depth than the WMAP values. And this, in effect, makes it easier for galaxies to reionize the universe. You need fewer of them. And so this is showing for the cosmic star formation rate density in red here, that you basically find a Thomson optical depth that agrees with the Planck result. But if you have this truncation at high redshift, it becomes a bit more difficult, and that's shown here. I made my own version of this plot just to illustrate. So if you have this sharp drop-off, then it becomes somewhat more difficult to reionize the universe. Again, there are a lot of uncertainties involved with reionization, with the escape fraction, clumping factor, different things, but it does make it a little bit more difficult to reach this level to find agreement with this Planck result. And also, one of the other uncertainties involved in reionization is the integration limit. So you have these luminosity functions, and you need to integrate down to the faintest galaxies that are known. The more numerous faint galaxies are probably responsible for reionizing the universe. Maddow and Dickinson integrated their luminosity functions down to 0.03 L star, Brant Robertson had to extrapolate a little bit, very reasonably so, to find agreement with the Planck Thomson optical depth. So, and just to show you that these are the constraints we have on these luminosity functions from Hubble programs at least, going down to the faintest UDF constraints so far. And so this faint end slope is really important. We believe that these large numbers of faint galaxies were responsible for reionization. With lensing, we can probe to fainter magnitudes still, as I'll talk more about in a little bit. And then, of course, with JWST, we'll be able to probe even fainter magnitudes, and they'll get tighter constraints on this faint end slope. We don't expect that faint end slope to continue forever. We expect that at some point we'll reach the smallest galaxies, that at some point galaxies that are too small will basically the supernova, for example, might blow out all the gas. We expect that at some point, there won't be galaxies. And we see some evidence for that in high-resolution simulations. This is from the Renaissance simulation, a paper by O'Shea et al. We see that around this, so around an absolute magnitude of around -12, we start to see this flattening. And so we don't expect this faint end slope to extend forever. And these are basically the limits that we can expect to probe with ultra deep field and lensing and JWST. And so we can almost start to get down to where we see this turnover, but not quite. With the local group, actually, we can do a bit better. This is a recent paper that came out by Michael Boylan-Kolchin with a couple of collaborators here with Ben Johnson and Charlie Conroy, showing that if you have this many faint galaxies at early times, you would expect to see them in the local group, the local dwarfs that are around us. And they find that basically this is inconsistent with the numbers of local dwarfs that you find. You require some flattening, similar to what was seen in the simulations, to account for the number of local dwarfs that you see. So let's dive into gravitational lensing. I've talked about how you can probe these fainter magnitudes with the power of lensing. So you see this galaxy cluster curving space-time, so that the images from this distant galaxy follow the curves in space-time, and they're magnified by this gravitational lens. These enable more efficient discovery and detailed analyses of the high-redshift universe. So here's a dramatic example of a lensed arc, and you see that this is work led by Karen Sharon, and the resolution that you can achieve for these lensed images is like having a 10-meter space telescope. You observe 100 parsec resolution at a galaxy at redshift 1.7. So this is something that we can't yet achieve, maybe someday. So cluster lensing, like I said, enables more efficient discovery of these distant galaxies. So these are luminosity functions. This is a fiducial redshift 10 luminosity function in a blank field. And here I've calculated what a lensed luminosity function looks like. And you can see that for any observed magnitude, for any depth of observation that you have, that lensing wins. It gives you more lensed galaxies than a blank field. Lensing doesn't always win. It depends on your redshift and your magnitude. So lensing basically wins at the brighter ends where galaxies are rare. And so that by going a little bit fainter in magnitude, you gain a lot more galaxies. At the fainter end, you either tie or you might do slightly worse. And it's because there's this trade-off. You're losing area due to the magnification, but you're also bringing more galaxies into view. So there's a competition there. And so again, when you're at the bright end, you win. And so at the highest redshifts that we're probing, redshifts 10 and 11, out to 12 maybe, lensing is the more efficient way of discovering these high redshift galaxies by orders of magnitude at the relatively brighter limits. So you heard Mark Postman talk about one such program to observe galaxy lensing clusters. One of Margaret's students back in the day, and my advisor at Space Telescope, and I did my second postdoc there. So he led the CLASH survey. This was one of the 3 multi-cycle treasury programs, along with CANDLES and FAT. 524 orbits on 25 galaxy clusters. Here's our team in London. And this program was actually the primary science goal was to study the clusters themselves and their mass distributions. And so you might have heard him talk about this here back in 2012. And so here are the 25 clash clusters. These are the Hubble images. Only these 5 outlined in red were selected for their strong lensing strength. And as he mentioned last time, and here the papers have now come out on the mass profiles. This was one of the key results from CLASH. There seemed to be some tension between simulations and observations in terms of the mass profiles. The observed galaxy clusters had denser cores than simulated clusters of similar masses. And with the CLASH program, we showed that this discrepancy went away, that basically the central concentrations agreed very well with the simulations. And you often hear, you always hear people say, we need more data to understand this problem. And I've said it a couple times. I'll say it, later. But I think, for this specific question, I think we got the 524 orbits. We've answered this question that the central concentrations of these massive clusters appear to agree well with the simulations. These galaxy clusters weren't specifically selected for their strong lensing strength, but they were massive clusters. They were very good lenses in their own right. They did discover large numbers of high-redshift galaxies. This is a paper led by Larry Bradley showing, again, these are the field luminosity functions in red at redshift 6, 7, and 8, and the lensed luminosity functions using the CLASH lens models. And you can see, especially at the bright end, you get good agreement between the lens model predictions and the observed number counts, showing that the lensing is significantly more efficient at finding these high-redshift galaxies than the field. And in fact, we found galaxies as high redshift as 9.6 and 10.8 lensed by these 2 galaxy clusters, which these 2 were actually selected for their strong lensing strength. So this is the redshift 11 candidate that Margaret mentioned. There are 3 lens galaxies of this distant 3 lens images of this distant galaxy, observing 97% of the way back to the Big Bang. And for each of these images, we see it drops out of 15 Hubble filters, and we see it only in the 2 reddest filters available with Hubble. Again, the spectrum is best fit by a galaxy at redshift 11. And just to show you, the colors of this galaxy are extremely rare. So these are the colors of all the other galaxies I measured in the CLASH clusters. At least I think the first 17 clusters are plotted here. And no other objects have these type of colors. We compared the colors of this galaxy to low redshift galaxies, brown dwarfs, hypothetical Oort cloud objects. We tried everything, and we couldn't find anything that matched these colors of these types of galaxies. And there are 3 of them in this one image. And their positions match with what you expect from the lens models. The lens models give you this extra confidence in the high redshift candidates when you observe these multiple images. If the galaxy is lensed by a certain angle, a deflection angle due to this galaxy cluster, if it's at higher redshift, then you'll expect to observe it at a larger radius from the center of the cluster just due to geometry. And so what we find is that, in fact, our redshift 11 candidate agrees with this redshift 11 determination based on the lens models, based on these other 20 lensed images of 8 galaxies at lower redshifts. And so the key takeaway from this plot, this slide, these curves are the critical curves at redshifts 2, 3.5, and 11. These are formally infinite magnification. And the takeaway is that this red line goes in between the redshift 11 candidates. And so you see the candidates on either side of that line. So it's not likely to be at redshift 2 according to this lens model. It's consistent with the lens model and with the photometry. It all points to redshift 11 for this galaxy. So 2 weeks after our paper came out on the redshift 11 candidate, there was a redshift 12 candidate that came out from a paper by Richard Ellis, detected in the ultra deep field. And I emailed him. I know Richard well. I congratulated him on his finding, and he said, he said they're not that certain about it because you don't necessarily expect a redshift 12 galaxy in the ultra deep field, and you only see it in this one filter, which means that there could be an extreme emission line galaxy that's concentrated basically all of its flux at this one wavelength. So basically, just redward of this filter. If you had flux concentrated in an emission line right here, then maybe that could explain this flux. And there were two papers that showed tentative detections of an emission line, possibly at a wavelength here, 2.7 and 2.2 sigma. So they weren't that confident. And I didn't bother showing them here, but they're possible detections. And so this is an enigmatic object. We still don't know what it is, but the fact that you only see it in one filter is a bit more uncertain. So we had to check whether the redshift 11 candidate could possibly be such an extreme emission line galaxy. We see it in two filters, but anyway, we thought we would check. It's unlikely that an emission line could reproduce the fluxes, but it's easier to check because it's lensed to 26th magnitude, so it's 3 magnitudes brighter or more than the ultra deep field candidate. We don't expect to detect Lyman alpha, so that's the normal way to confirm these high redshift candidates. The highest published spectroscopic redshift from Lyman alpha is 7.73 from Pascal Oesch, and this is the detection here. It's actually increasingly difficult to confirm galaxies at higher and higher redshifts. We believe because we were looking through the neutral IgM. The universe hasn't completed reionizing, and so we don't expect to detect Lyman alpha, but I do expect to detect the continuum break. So we have a program with the Hubble Grism, 12 orbits, to basically, this is the expected signal that we expect to see, and to rule out such a strong emission line or multiple emission lines that could somehow be confusing us. And so we've now ruled this out. We have all the data in, and even based on the first epoch of data, the first 4 orbits, and this is an example to show what the Grism data looks like. You basically take all of the light and it spreads it across the detector, and you get a spectrum for every object in the field, but they're overlapped, so the analysis is a bit tricky. So we have 2 of the best experts working on this. Nora Perskal put out a paper recently showing that you would expect, if there were such an emission line, you would expect to see a bright detection, which you don't see. So you see this. It's not. This isn't the cleanest epoch, but you expect something. So this is the model, and this is the observation. And so based on all of these overlapping objects, you expect to see something right here, and you do. And the subtraction isn't perfect, but you don't see something that's not accounted for in the model, basically. So the fact that there's something here, this isn't the best example. We have 2 more observations, 2 more epochs that make this point even more clear. But we do rule out the emission line, and it is shown again from the final 2 epochs of this observation. So this is a plot from Gabe Brammer showing again these are preliminary reduction of this data. It's challenging work, but basically the purple line is what we might expect for a galaxy at redshift 11 or so, and the red binned points are the observations with all of the contamination subtracted. And so I would say, so far we see something, consistent at these wavelengths, but we also see some extra flux at lower wavelengths, and we also see something, consistent with noise so far. I think we're working more on the, on the models and trying to understand this contamination of all these overlapping sources. So it's, this is challenging work, but we're, so far the signs are still, consistent, I'd say, with the redshift 11 candidate. I also have 100 hours of Spitzer imaging to follow up this candidate. It happens to be 2 arc minutes away from an 8th magnitude star, which, what are the odds that the most distant galaxy would be, very close to a star you can almost see with your naked eye. But so there is a lot of scattered light that makes it more challenging in the Spitzer images. There's a lot of background here, but so far, what we find is that in the shallower Spitzer imaging, there appeared to be some hint of a Balmer break, suggesting an older population. And now with the deeper Spitzer imaging, we've shown that it's more consistent with a flat spectrum, so a younger population. And we don't have very strong constraints yet. We're working to subtract the light from this star and really understand our backgrounds here. But so far, we've shown that it's consistent with basically a young population. And so there'll be more results on that to come. So again, we have these two high redshift candidates from Clash. So let's look at the big picture here. We have a candidate at redshift 9.6 and a candidate at 10.8 lens to form these images. So this is redshift versus magnitude. And so only a handful of candidates have been discovered at redshifts greater than 9. We have two more sort of less secure candidates from Clash. They're a bit fainter, less confident. From the field, UDF and candles, there are also a number of candidates. And then from the frontier fields, there's one that's been published at a redshift of about 10, which I'll talk about in a little bit. But altogether, around 14 candidates at redshifts greater than 9, compared to around 200 at redshift of 8. So this is really the frontier in terms of high redshift galaxy studies. So when Matt Mountain asked us, the director of the Space Telescope Science Institute, up until recently, he's now taken a position at AURA, the head of AURA. A few years ago, he asked, what can we do to improve on the Hubble Deep Field programs before the launch of JWST? So there's been the Hubble Deep Field North and South, the Ultra Deep Field, and the optical and the infrared. And so when he asked, what can we do next? What can we do to improve on these? We had a suggestion to use cluster lensing. So this is a white paper we submitted to this science working group. And so they fielded some, I think it was 37 white papers on different ideas to observe more blank fields, lensed fields with imaging or spectroscopy. And we submitted our suggestion to use lensing clusters. And ultimately, they decided to do both clusters and blank fields. So they're, with the two cameras on the Hubble Space Telescope, the advanced camera for surveys and the wide field camera 3, they're observing clusters and blank fields at the same time, and then switching the cameras to observe the others. So this is an 840 orbit director's discretionary program with Hubble, and up to 1,000 hours with Spitzer director's discretionary time. And the full program is observing 6 galaxy clusters. The first 3 have now been complete with Hubble, and Spitzer has observed all of these. So 6 blank fields and parallel fields to come. And we have, if you saw my talk at lunch, you heard me talk a bit about the frontier field lens models. So this is a lens flow image I made, inspired by the Planck polarization maps you may have seen. Magnification is the color scale, and the flow is the direction of the lensing sphere. We have these lens models available for all of the galaxy clusters to level the playing field, so that anyone, you don't need to be a lensing expert to use this 840 orbits of director's discretionary time. All of these lens models are available, and this is work that I coordinated, and I've made these available to the public. So a lot of great work from the community was done here. And so as I said, so the Hubble Frontier Fields observations are now halfway complete. Here we are today. The first 3 clusters are complete. The 4th one is ongoing, and we have 2 more to go with Hubble. And Spitzer has observed all of these clusters so far. So what do we see? First, so the frontier fields should really answer this question of whether there was a gradual or more dramatic evolution in the first 500 million years. So this is a plot from Pascal Oesch showing these hints of dramatic evolution. And this is actually my Clash data point at redshift 11 with huge error bars, because there's only one object constraining the cosmic star formation rate density. So we should, and these are based on my estimates, we should either expect 70 galaxies at redshift greater than 9 or 13, give or take, from the full program, depending on which of these universes we live in. And so here's a plot from our recent paper showing this again. 70 or 13 at redshifts greater than 9. And this is to show that the lens models all yield consistent predictions. So the lens models don't introduce any unnecessary uncertainties in this. We're really going to get a clean measurement of what the universe is doing at these early times in terms of galaxy evolution. So what do we see? Abell 2744, the first frontier fields cluster, actually appears to have somewhat of an overdensity at redshift of 8. We see what might be a protocluster in the corner there. It's a bit difficult to say for sure with photometric redshifts, but nothing like this has quite been seen before. So a healthy number of redshift 8 candidates, nothing above redshift 9. In the blank parallel field, we see this one candidate at redshift greater than 9, perhaps boosted a little bit by this one elliptical galaxy here. Maybe it has a little bit of lensing effect. Here's a close-up on that galaxy you see here, this little red smudge. Here's the spectral energy distribution fit that I made to this galaxy and its redshift likelihood. Okay, so one galaxy redshift greater than 9. Remember, I expect optimistically 6 per field in the clusters and in the blank field, so 6 per field. Max 0416, the second cluster. Again, redshift 8 candidates, nothing above redshift 9 that I find. And in the blank parallel field, redshift 8 candidates again. Even, up to redshift 8.7, so close to redshift 9, but not quite above redshift 9. The third galaxy cluster, I don't find anything much above redshift of 7.5. Interesting. This is a very strong lens, but we may be, observing a void in the distance. In the parallel field, again, a few redshift 8 candidates, nothing above redshift 9. And so here's the big picture here is I'm plotting all of these galaxies from these first 6 fields, their magnitudes versus, their redshifts versus magnitudes. And so above redshift 9, we're halfway through the program. I expect somewhere between 6 and 35 redshift greater than 9 galaxies. So far, we find this one, at least in this detections that I've mentioned here, down to a magnitude of 28.7, where I've done my estimates. Now, you have to worry, am I missing some? And surely I am. This was a pretty generic detection that I ran with Sextractor that I did from these previous slides just a few days ago for these slides that I'm showing here. So I'm also simulating the completeness. So I have galaxies that I've placed on this grid, and I've de-lensed them and re-lensed them again, and put them into the image. And so I'm quantifying what is the completeness. When do I detect the galaxies, and when do I miss them? And so I'm still working on this, but other people have been working on this a lot too. And here's a paper by Adi Zitrin showing a redshift 10 candidate that I actually missed. It was discovered, I believe, by Wei Zheng. Actually found this galaxy in his catalog. This image right here, it's very close to these other objects, so it kind of gets lost a little bit. It's right next to a diffraction spike here, but it's not part of the diffraction spike. I think we're pretty confident about that, but it's just off to the side. And so you can see that it's the point here is that it's challenging. And so they detected this one object in their catalog, and then they were able to, based on the lens models, find these other two, by eye at first, and then by carefully subtracting off the nearby objects. And so here's to show a little bit more detail of how they do this. They use a smoothed images, I think median filtering they used here, and so they're able to better detect these faint objects. The A, B, and C here. Rachel Livermore is also doing very sophisticated work with wavelet decomposition. So decomposing the images into different scales, basically, different wavelengths, if you will, across the images, and showing that you can achieve much better depth in the image. These are the magnitude depths that she recovers from the initial images before she does her analysis, and then in the final processed images after she accounts for all these different structures on different scales. So we do require improved detection schemes. I think these will help uncover more candidates. So Hakeem Atek has done a method I think similar to this one, and he's found galaxies fainter than observed in the ultra deep field. I find some galaxies like this fainter than any that we've observed before. These are the faintest intrinsic sources. So this is one of the main goals of the Frontier Fields program, and we can see it being achieved, that we're probing the most distant galaxies yet known, and we're improving the constraints on this faint end slope that seems to be consistent. It's still rising. It still has the same slope out to these fainter intrinsic magnitudes. And so here I have an update on one of the previous redshift 9.6 candidate from CLASH. This is from Wei Zheng that I mentioned earlier. This is in the 4th Frontier Fields cluster. So I showed the first 3 in the previous slide. So this is now the 4th Frontier Fields cluster. This is the fit to the Hubble photometry at a redshift of 9.6. Now in the deeper imaging, it appears to be at a slightly lower redshift, 9.2, I'll flip back and forth a little bit. So the likelihood distribution is still consistent with what it was before, but the photometry is a little bit noisy and appears to be a little bit lower redshift. And I even find a little companion nearby. I'm not calling this redshift 9 cluster, but there appear to be these two galaxies at least nearby, 15 kiloparsecs away from each other, lensed. So you would divide that by the factor of the lensing, which is, I think for this galaxy, it's around 10. So maybe they're separated by a kiloparsec or so in the source plane. So there is, so there's 3 so far in the frontier fields, galaxies of redshifts greater than 9 that we know of. Nowhere near the 70 yet that we expect. And so this is, right, and so just to summarize, I think the frontier fields are certainly finding galaxies fainter than have been observed in the ultra-deep field. Ultimately, this is another plot from a recent paper of mine on the predictions and early results showing that ultimately we do expect to find galaxies 10 to 50 times fainter than the ultra-deep field based on the full program. And these are just number counts versus intrinsic magnitude, unlensed. And again, we expect to find strong constraints on this evolution at higher redshifts. So what about beyond the frontiers? There's Euclid and WFIRST and WISH. There's other large, wide field space-based surveys, observatories that are planned for the future. WFIRST, for example, these are estimates that I made for the WFIRST mission. Hundreds of thousands of galaxies at redshift 8. And perhaps out to redshift of 15, depending on, again, what kind of universe we live in, what the evolution is at these high redshifts. Many galaxies, now it would be useful to find these before JWST so that we could study them in more detail. I think Euclid will probably have some overlap with JWST, but WFIRST, it's not clear. But there's a lot more we can do with Hubble, fortunately, to find the best and brightest high redshift candidates for JWST to follow up, and also to follow up now in more detail. So here what I'm plotting are the results from CLASH, or these are actually based on the CLASH lens models, and as I showed before, the number counts agree with the lens models here. These are, the dashed lines are blank field luminosity functions, and then the solid lines are what we expect from lensing, so more efficient than the field. And this is a recent Planck data release. These are galaxy clusters they've detected based on the Sunyaev-Zeldovich effect. And so they've mapped the whole sky to everything except low galactic latitudes. They found over 1,000 clusters that are now confirmed with redshifts and mass estimates. And this is to illustrate that the CLASH survey, again, it selected massive clusters, but they weren't the most massive. They weren't necessarily the strongest lenses you could possibly observe. With a new Hubble survey, which we proposed this cycle, along with Christine Jones-Foreman here and others, you could observe all of these highest mass clusters, and then which are which are more efficient lenses, and also some lower mass clusters which already have Hubble imaging with ACS. We know that they're strong lenses, and you can observe them in the infrared very efficiently. So there are a lot of clusters that that don't have infrared imaging. They're spectacular lenses, but they haven't yet been searched for high redshift galaxies. And so with a program like this, you could expect something like around 100 galaxies at redshift between 9 and 12. So much more than the 30 that we have currently. And right, so these most massive clusters, they include clusters like the Frontier Fields clusters, the Bullet clusters, some of these most spectacular lenses, and there are many more of them that don't have infrared imaging yet at these highest Planck masses. So I think the time is ripe now to harvest these clusters that have been identified and to use them as cosmic lenses, study the distant universe, identify the best and brightest redshift galaxies, and also to characterize these lenses for use now and also before JWST, so that we can use them in the future to study the distant universe. Once you have brightly lensed galaxies like this at high redshifts, you can do all sorts of things to study them in detail. These are some recent results. There was recently an ALMA detection at redshift 7.5, suggesting an evolved dusty population, even at these early times, perhaps surprisingly evolved. At the same time, you find possible hints of very pristine galaxies in the early universe. This is a galaxy at redshift 6.6 with a possible pristine population 3 component. It's not that conclusive, but there's a suggestion. There is a helium-2 detection at 1640 angstroms, and with a pristine component here and more enriched components off to the side, resolved in Hubble imaging. So you can study these candidates in more detail and study the evolution of galaxy enrichment from more pristine galaxies to more dusty evolved galaxies. And you can also confirm them. As I mentioned before, you find the highest redshift galaxy confirmed with Lyman alpha is at the redshift 7.7. Beyond that, it's difficult to use Lyman alpha because it's absorbed by the neutral IgM. By finding more brightly observed ones, we expect to push this out beyond redshift 8 in terms of Lyman alpha. But you can also use other emission lines with high ionization states, such as carbon-3 at 1909 angstroms, which is redward of Lyman alpha, and so it's not absorbed by the neutral hydrogen before reionization was complete. So in principle, you could use this line out to higher and higher redshifts with JWST, for example, and even current instruments. So this was a section, I believe this is from Mossfire. And the line is much weaker than Lyman alpha, but it's not absorbed by the neutral IgM, so you can push to higher redshifts. So this is carbon-3, doubly ionized. Dan Stark also has a detection of carbon-4. Just the other day, this came out at redshift 7.045, so triply ionized carbon. So very energetic photons that suggest a lot more ionizing flux to reionize the universe by these high ionization states. And so we really need to find these best and brightest high redshift candidates now to study in more detail now, like I showed, and also in time for JWST. So the JWST is scheduled for launch in October 2018, and the first call for proposals is November 2017. So it's fast approaching. If you're on a GTO team, it's even sooner than that. The proposal that we put in this cycle, the observations will span from October 2015. They'll end in September 2016. So if we want to deliver these candidates to the community and these lens models in time for JWST proposals, this is basically, we're running out of time, and we really need to do this now in order to have time to analyze these data and provide this to the community. And so that's it. I'll just leave you with my conclusions there and take questions. Great, thank you.
Well, I have to say, it's amazing. I mean, some of us were saying when we first came in, but in the ancient days when we were students, the galaxy of the redshift we have in the New York Times. They're the highest redshift galaxy ever.
And now they're the best lenses.
It's an amazing part.
And now they're the lenses.
Now they're the lenses.
Right?
Yeah, so questions for Dan. Yeah,
I have a question regarding the photo-Z techniques.
Right.
Recently, maybe you've heard of it from Franz Bauer. We had a campaign with Mears and Magellan, and one of the most solid photometric redshift determinations at redshift 7.7, I think, turns out to be a T-dwarf, because we T-dwarf in the thick disk. Right. Because we detected continuum and we see clearly those deeps in the SED. And it turned out that those stars were not in the libraries of templates. Right. And so they were just not considered by the technique. How do you think it might affect the results? Of course, it won't be a big problem for multiple images because it's very improbable to have them, but for single source detections.
Right, I considered brown dwarfs in my paper. It's 20 pages on a single object, and I considered brown dwarfs down to anything cooler than what we'd observed yet. So I went down to, I used both spectra that had been observed and then models down to 200 Kelvin, so Jupiter's basically, and none of the colors matched for that object. We had based on the Hubble and Spitzer photometry. You're right, in general, this is something that people need to keep in mind, especially at the relatively brighter magnitudes of 24th, 25th magnitude, where the scale height is such that you expect to have some contaminants. At 26th magnitude or so, I understand that you don't expect as many contaminants in terms of brown dwarfs. But there are people do include them in their modeling. A lot of times that they'll fit to galaxy colors and also brown dwarf colors. And every once in a while, I'd be interested to look at that one in more detail and understand exactly what went wrong there. I mean, every once in a while, the photometric redshift can give a certain answer, and maybe there'll be a lower likelihood peak at a lower redshift, or that a brown dwarf could possibly be a solution. I think one issue is that sometimes you'll have I don't know if I have an example here, but you'll have a likelihood distribution that it could be at high redshift or a low redshift, and people just take the high, the most likely value, and they kind of run with that. I don't know what the case was in that one, but I've tried to be careful in my work to show what's the likelihood that something's at high redshift, so that people don't get too discouraged if it turns out to be at lower redshift. So it's a good question.
Yeah.
So
Yeah, I don't know your name, sorry.
I'm Sally.
Okay.
So not to make this about brown dwarfs, but now that white dwarfs are actually being found, there's a hypothesis that the spatial and velocity distribution of white dwarfs is much different than for LMT dwarfs, that they're cold because they're old and therefore they're falling in from the halo. So maybe, I don't know if the spatial distribution of the white dwarfs could be a clue, because some of them might be in the temperature ranges that you're looking at, but
Right.
So you might have to worry about that no matter which direction you're looking.
Okay, so we might have to worry about even more than what I suggested for I don't know if the mics are picking up the questions well, but I think, and in fact, some of these high redshift programs like Borg, I know Michele Trenti is very interested in looking for high redshift galaxies, but also looking for brown dwarfs and studying their scale heights. Maybe you were even referring to that work or work by others, but yeah, that's a good point.
Seth.
thanks. So you said there are 14 Z of 9 candidates now and like 200 Z of 8.
Right.
So can one correct for the selection functions and completeness enough that you can then move that ratio into something that actually might tell you what the true ratio of objects at redshift 9 to redshift 8 is, or are we just not there yet?
Let's see if I understand your question. I mean, if you extrapolate the luminosity functions down, we are seeing a deficit compared to what you expect, and these are Schechter functions with the 3 parameters, and you're evolving those according to redshift. But I'm not sure if I completely understood your question.
I mean, so I guess if you could see all the galaxies at redshift 9 and redshift 8, you know the ratio. And
right.
Presumably we're only detecting some fraction, but
right.
I guess the simplest hypothesis would be that we're missing the same fraction of those 2 redshifts, so that the ratio 14 to 200 is still accurate.
Right.
But obviously.
Yeah, people do have to, I should have mentioned, it's a good point. I mentioned incompleteness due to a galaxy, falling on top of another galaxy, and you don't see it that way. But you also have to account for the redshift incompleteness. If a galaxy is at a certain redshift, maybe it's less likely that you're detecting it. Maybe surveys are more sensitive to some redshifts than others. In fact, there is some difficulty at around at redshifts greater than 9, where they could be contaminated by lower redshift galaxies. And I'll see if I have if I can stop this plot. No, not quite. But I may have oops, I didn't want to do that either. I may have well, I probably have a slide there somewhere that shows basically the spectral energy distribution is rising. Still go. All the way through the Hubble filters. That you basically have at redshifts greater than 9, the flux would be dropping out of each filter successively. So the spectrum is basically going up. And so that could be confused with the lower redshift galaxy. And so we have to make sure that we don't have higher incompleteness at these high redshifts than we did at redshift 8. That's a good point.
So Dan, I want to ask you a question. Suppose you make all these observations and you don't find even your 7 or 9 galaxies at a redshift of 9 in each field. What will you conclude?
Right.
What will that tell us about galaxy formation? Or what does it tell us about our ability to learn about it?
I think assuming that we're detecting them well enough, and assuming that we're not just missing them, which I think I think that we've been using this technique for a long time, and many of the high redshift candidates that we detect, do end up being confirmed. Every once in a while, something goes wrong, but I think we've shown the technique is robust as we go to higher and higher redshifts, and we're confirming galaxies out to redshift 8 now. And we don't expect that to break down at redshift 9 or greater. But if we really do see a drop-off, then that suggests some dramatic evolution is really going on, and we might be on the cusp of observing the first, burst in the formation of galaxies, the first surge in the galaxies really building up at early times.
I mean, could it be for some reason they're very low surface brightness when they form? I mean, you have a strong surface brightness sensitivity, right? I mean, would you? Right.
So, and in fact, the ones that we've detected so far are very compact. And so you might ask if we're more, biased toward detecting those, and they're more, maybe they have lower surface brightness wings that we're missing, and we surely are.
Some of them are only.
Right. And so. Yeah, and so we think that, the galaxy sizes on average, the ones that we detect, the galaxy sizes decrease as we go to larger radius. And so radius, thank you. The radii decrease as we go to high redshift. And so when we try to estimate our completeness, a lot of times we'll put in a profile, so a STScI profile, a Dvorak profile, and it'll have a certain radius. And that's not exactly what we should be doing. It doesn't just have one profile. Maybe it's clumpy, maybe it's more diffuse, maybe it has more spread out. And so maybe we're also underestimating our completeness to some degree. So that's a good point.
So, one more question? Yeah, Charlie.
I just have a question about your Z11 galaxy.
Right.
When you put it on the Medell plot,
Right.
Presumably you're measuring a monochromatic flux that's in rest frame is UV, and you have to convert that to a star formation rate.
Mm-hmm.
And I guess you use some standard population synthesis. Do you include extinction in there or metallicity? And what kind of IMF? You assume a fully sampled IMF?
Right. So, yeah, we do have to. I'm trying to see if I can pull up the plot. Yeah, we do. Yeah, this one's just gonna keep going. Yeah, we do. It is one galaxy, and so we only have so much of a constraint on the. I'm not finding that plot. Anyway, let's put up a different plot. I'll put this one. So it's one galaxy. We're doing a lot of extrapolations, and right. So we have to convert the UV flux that's assumed here into a star formation rate, and we don't expect much dust, and we don't measure much dust at these high redshifts. We find that galaxies are getting bluer. We think there's less dust as we go to higher redshifts and also to fainter magnitudes. And so we don't include much of a dust correction. This is consistent with what we observed based on the Hubble and Spitzer photometry of this galaxy itself. I have in my paper, I didn't put it in here, but constraints on basically on the extinction. So I try to, a grid of models with different extinctions and star formation rate histories. And so we don't expect a lot of dust. We don't think that affects our uncertainties on this. The uncertainties on this are dominated by the fact that we have, one galaxy at redshift 11. So there are huge error bars in trying to extrapolate the luminosity functions. But you're right, we need to make certain assumptions also about the IMF.
Right, in your star formation history, you must have put in a short time duration, I would imagine.
Yeah, I tried different, so I think, the preferred models are actually rising star formation rate histories at early times. We think in the local universe, we have a lot of times you model galaxies exponential decays, and in the early universe, there's a rising component. And I tried the whole range of these, types of models, and the data really isn't there to put very strong constraints on the star formation rate history with Hubble. With JWST, we'll get much better constraints.
Just keep in mind the age of the universe then was 500 million years. So it's basically a very short episode.
Well, that's what I'm saying. It must be short of what the normal calibrations would be.
Right.
Okay, let's thank Dan for a spectacular.